Alright, hello everyone. In this video we shall go over our first operation from the multivariable calculus that will be helpful in our understanding of transport phenomena. So introducing the gradient, sometimes it is also referred as the del operator, and it has this symbol, this upside down triangle. I don't know what's the correct terminology for it, but I'm gonna make do anyway. It's called the del operator, I believe, and I'm sure that's the correct terminology. Gradient, del operator mean the same thing, and sometimes it's also written as, just to show you, the gradient. If someone says gradient of f, this might also be written as grad of f in some texts, but we're not going to deal with that. We're just going to stick with this notation. Okay, all right, perfect. So in order to illustrate what this means, we have I have an example of the temperature distribution. This right here is the temperature distribution in Cartesian coordinates. Temperature distribution. Okay, distribution. So imagine, I want you to imagine something like a rectangular slab. If only I can draw it today. Okay, now this equation right here, t of which is the function of x, y, and z is equal to 3 times x squared plus 2y plus z cubed. All right, so that represents how the temperature varies. Oops, that's going to be the z-axis. How the temperature varies inside this slab. Okay, now this equation models the temperature profile in this slab. Okay, now let's see. I need my derivatives, my partial derivative with respect to x, my partial derivative with respect to y, and my partial derivative with respect to z. Okay, and if you guys remember the definition of partial derivative, so you take derivative by holding everything else. If the partial with respect to x treats everything else as a constant, so this is just going to come down to be 6x, and the partial with respect to y is going to come out to be, so 3x squared is going to be a constant, z cubed is going to be a constant, we're left with 2. And similarly, the partial derivative with respect to z is just going to be 3z squared. Okay, so now we have the partial derivatives. All right, good. Our next step, the definition of the gradient of temperature. All right, the gradient of temperature is a vector, is itself a vector expression. Okay, so you have the gradient itself. Oops, let me get rid of that. The gradient of t is a column vector. It's represented as a column vector. Okay, and on the top I have this right here is my x component, my y component, and my z component. All right, so my 3 components listed from top to bottom. Now, according to my expression, the expression for partial derivatives that I already have derived, the gradient expression comes out to be 6x, 2, and 3z squared. Now, the gradient itself is always going to be a vector quantity. Okay, the gradient itself is always going to be a vector quantity. We know that temperature is a scalar, but the gradient of temperature is a vector. All right, we've learned about the computation of how to compute a gradient, but we're also concerned with the what does it intuitively mean? What does gradient of t represent? So gradient just represents, it gives you the direction of the gradient. It is in the direction of the steepest change. Okay, so all these vectors, you know how your temperature is varying with respect to x, you know how your temperature is varying with respect to y, and you know how your temperature is varying with respect to z. And all these 3 expressions are collected as vector quantities now, and the direction is going to be in the direction of the steepest change. And just to make it even more visual, let's say I have a mountain, right? That's my attempt at drawing a mountain. All right. So this is the front view of the mountain, all right? And if I want to climb this mountain, I'm somewhere here. I obviously want to go in the direction, of steepest change, the steepest ascent. All right, that's the direction I want to step in. All right. And if I were to draw contour plots of this mountain, the contour plots, all right, what does that mean? So basically what I'm doing here is I'm taking a top view. I'm taking a top view of the mountain. And this right here represents z equals 0. This is starting at ground level. And you're going at z equals, let's say, 1 kilometers, 1 miles, whichever units you want to use. This is z equals 1 kilometers. And just to make it visually more appealing, this is z equals 1.5 kilometers. So as you can see, as you're moving into these contours, your height is increasing. So if I were to draw the direction perpendicular to the tangent at any given point, all right, I'm drawing all these vector arrows. They're all perpendicular to the contour. They're all perpendicular to the contour lines, as you can see. Okay, and just to even emphasize it further, all of these vectors are pointing in the direction of steepest ascent. Okay, the steepest ascent. Now the height of the mountain is a function of both the horizontal distance and the vertical distance, right? It is a function of both x and y. The gradient of height is going to be the partial with respect to x and the partial with respect to y. And this right here, if you take the gradient at any given point, that's going to show you in which direction your steepest descent is. That's going to show you in which direction your steepest ascend is. All right, that's the direction in which you're going to step, if you want to climb the mountain fastest. All right, now why is gradient important? Why study gradient? Why gradient is important in transport phenomena, important for students of TP. All right, now some questions. I'm gonna ask you some questions. I'm gonna just make some statements where heat transfers from high temp to lower temp. Okay, we know that diffusion occurs from high concentration to low concentration. We know that intuitively. We've all observed that in our beverages, the cooling of our coffee, etc. And in order to model these in 3D, we're gonna say that the heat flux, the rate of heat flux is proportional to negative of the gradient of temperature. Similarly, mass flux of a certain species is proportional to the negative gradient of the concentration of that species. Okay, so keep in mind, the gradient itself tells you the direction, the gradient itself shows you the direction in which steepest change is occurring, and this negative right here shows you that we have to go down the gradient. Conduction, heat transfer is down the gradient, mass transfer is down the gradient. All right, just a quick recap. We learned how to compute the gradient, also known as the del operator. on this on this temperature profile, on this simple temperature profile in Cartesian coordinates, and we came up, this right here is the definition of the gradient. All right, this is the definition of the gradient, and the gradient itself tells you the direction of the steepest change, and the magnitude tells you how fast, like the rate at which you're rising. Okay, and this right here, we talked about a mountain, and hopefully this was able to give you a more intuitive feel of the gradient, of the physical meaning behind the gradient. All right, and hopefully this last conversation bridges the gap between multivariable calculus and transport phenomena. Our rate of heat flux is going to be down the temperature gradient. Our rate of mass flux is going to be down the concentration gradient. I hope this was helpful, and I'll see you guys later in the next videos. Thank you for your kind attention.